don't talk about the stuff that I just talked about. There you go. So take a look at a couple things, trying to organize. Here's where they are in an equation sheet. I think this might be a little old, so I think I got rid of the apostrophes. I don't like the apostrophe things. I prefer to have the use numbers. I think I did that on there, but on the equation sheet. But make sure in your exam prep that you're using this so you feel comfortable. It's like a lifeline kind of thing, right? Doesn't have every equation, but one of the purposes of having an equation sheet is so you don't go like equation hunting, right? So I didn't want to put too many equations on there because you spend too much time trying to search for the right equation, or even use the phrase, I didn't know which equation to use. I don't want you to think in those terms.
All that bottom, it's just not on the equation sheet anymore.
This guy?
No, we have the particle, so the underneath, the oblique central impact, those equations are not on our equation sheet. We just have the coefficient of restitution.
Yeah.
Just so you know.
Oh, okay, cool. Yeah, I think, I decided to make that like better. Yeah, I thought that was a better thing to do. Okay, so yeah, I should change this so you're not thinking.
Well,
We should get the thing.
We should know that.
You should know that. Yeah, you should know all that. Yeah. It was because I was trying to fit something else on. I don't remember. So I didn't update this slide. But I'm just trying to encourage you. This is the section that we're doing, right? For this. So ask yourself, that's why that's funny. You have to explain why it's funny. It's not funny. Okay, never mind. We'll talk more about those things. So what kinds of problems have we covered since exam 1? We did particle of Newton's second law. I think this is true where we did class 6 and homework 6 was rectangular coordinates. Class 7 and homework 7 was path and polar coordinates in F equals ma. Then we had particle work and energy. So we had class 8, homework 8, where we had potential energy, kinetic energy, work added, and friction loss. 9, we did conservation of energy, power, and efficiency. So we had kind of more work energy, but we added in the ideas of power and efficiency. Impulse and momentum, we did class 10. Force, time is the impulse, mass times velocity is the momentum. And then class 11, we did collisions and the coefficient of restitution. And there should not be a class 12 here. Okay. So organizing your brain is what we're trying to do here. So organize the work that we've covered. Exam 2 is on 6 classes, 6 topics with 6 homework assignments. And these are them. I can post this if you want. You don't have to write all that down. But I would encourage you, this is Dr. Deal's personal experience and how he became moved from being a C student to an A student. I started organizing myself when I was doing exam prep and write down all the stuff that we had covered, right? And then when I went to go prepare for an exam, I'd make sure that I would give it each one of these things, it's kind of its due course, right? And then I would look for other problems, a lot of times out of the textbook, and say, can I do this problem? How do I go about doing this problem? And there's often, I usually pick ones where the answer's in the back of the book, and then I try to aim for that. That's a lot of time. It's time consuming. It's not very efficient. So I gave you other, example problems to do. I'd rather leave those for you to do as opposed to do them today and take the risk, big risk for a professor who's nervous in front of people, and just pick some problems. You say, hey, I'd like to see this. And then maybe I would suggest that we pick a random problem and just try to work it out. It's going to be probably longer than an exam problem because most of the problems in here are kind of tough to finish during an exam. But we lift to the heavy weights so the light weights seem so much lighter, right? That's my approach. So, and then solving the problems. But I also thought, and I mentioned this to Brett not long ago, that I thought maybe another technique, because I'm trying to improve all the time, trying to address the things that I see that are common for all students, right? You're not alone, you have the things you struggle with are the same things all students struggle with, is that problem identification. So maybe just look at the problem and not even work it all the way through, but just say, what's going on here? And work through the mindset, right? I want you to work through that, right? To get better at problem identification. What's the nature of it? And then the next step is, how do I go about this? What's the first thing I should do? What's the next thing I should do? And how can I approach a problem so that even if I don't know how to solve it when I first started, I can get myself in a position where I'm gonna go, midway through, I'm gonna go, oh, I got it, I know how to do this now. That's the main thing we're out to try to do, so I don't know how to teach that most effectively, and I'm prepared to change up what I'm doing so that I could better do that. So I could get you so that you're better at it. So anyway, that's some ideas that we could do today, but also I'll just answer your questions. You say, hey, I would like to see this, I'd like to see this done from homework this, I didn't get that from homework whatever, and we can go from there. So how do you want to proceed? Here are problems that are on the, let's see, so we have a kinetics with rectangular coordinates. This is from spring 2016, so it's a problem I asked. It looks like a problem I put together.
Test question?
Pretty much identical to the example in the book, an example in homework. I mean, during class. There you go. Right, words. And actually, they're kind of numbered poorly. 16, I don't know what the hell that is. 17, oh yeah, I remember. I think that we used to combine particle kinematics and the first part of particle kinetics on exam 1. And I decided to roll that back and make exam 1 all particle kinematics. That's why they're numbered weird on this. But they should be numbered differently on yours. So here's a rectangular coordinates constrained motion, kind of combine. You might lend yourself to think that this is a work energy problem, but of course this has used Newton's second law. One of the differences in work energy problems is they're usually between 2 points, but as opposed to being Newton's second law, which is instantaneous, right? We want to find the acceleration right in there. And also if they ask for like a tension, that's also quite often. Doesn't have to be, but could be. So here's Newton's second law, where we're using path coordinates and some fundamental kinematics right there. So yeah, so what's the minimum velocity for the ball to make one revolution around the circle? All right, determine the equations of motion. All right, here you go. Here's also Newton's second law. Here's with path coordinates. Here's another one with path coordinates. Right here, so here's one with work and energy. It's got some springs involved. Got a coefficient of friction, so we got to worry about the friction in there. Here's an impulse and momentum. It's really a collision one because it's got coefficient of restitution. You can see that kind of boom, jumping out at you. Work and energy problem. Even tells you how many points they were worth. By the way, those points might be larger because this was a 50-minute exam. Right, all the ones at Coast Guard. The dynamics was a 3-day-a-week class, so every class was 50 minutes. So sometimes there'd be less, there'd be less problems.
Can we just run through the setup for a coefficient of restitution problem?
Okay. Want to pick a random one?
Yeah.
Out of the book?
Okay. Anyone is fine. I just kind of need to algebra.
Gotcha.
No,
okay, so let's hopefully this camera here, which I'm way behind. I had a student that wanted to talk about something, so I didn't get to eat my lunch all the way through and get on the prep for this, so gotta calm down.
Can we do the one ball bouncing from earlier in the slides?
Okay, well, this guy right here?
That one.
Okay, let's do that one. Cool. All right, so let's see if we can get my camera working here. Camera. Boom. We don't want that camera. We want this camera. Boom. Okay, cool. So, exam 2. And here are Z problems. Oh, there you go. Nice. Blank? No, not blank. Ooh, I rewrote everything out. I wonder if I posted these. I bet I did. Maybe not. I didn't like the way that some of the old solutions were looking. I have been meaning to for a while to update the scans of the solution so that they would do it the way that I would have done it. You had to ask for the problem, and I don't see it. It didn't
So
jump
they
out.
do a different one, I really don't care that much.
No, it's a problem, man. I'm just sorry, my brain's not functioning. I can't. Which problem was this? Let's see, how far into the thing was it? Maybe it was near the beginning. It was like right after that. So why don't I see it?
That's fine. Did we do anything? That was 75 grams, not kilograms.
Yeah.
Why would they do grams? Because they're maniacs. I don't know. Is that what you were asking?
Kind of, yeah.
Okay, so you must use impulse momentum here. I don't know. This is either, I think this is Alicia. Alicia wrote this. So you must use impulse momentum to receive full credit for this problem. A 75-gram ball is projected from a height of 1.6 meters with a horizontal velocity of 2 meters per second and bounces from an 400-gram smooth plate supported by springs. Knowing that the height of the rebound is 6 meters, determine the velocity of the plate immediately after the impact, the coefficient of restitution between the ball and the plate. Okay, there's only two things. All right, so. We don't have to. You were saying you wanted the setup of this more than necessarily working it all the way through.
Yes. Something that I struggle with too is like knowing the step-by-step methods. Yeah, because there's a lot of like intermediate math that I feel like kind of gets lost in translation.
Okay.
Yeah, like the one where we bounced it off the wall, the homework problem.
Mm-hmm.
Yeah,
The two
that-
polar coordinate transformations, like that one, it threw me for a loop because it's, you know,
That one
you have
was
to do
quite
two, so I'm like,
quite confusing.
There's.
And the question's having a second part after like the efficiency is also just.
Yeah, I get you sometimes, but I mean, I have like a list. I have like a list of priorities that I want you to be to be able to do, and sometimes I think, well, I want you to have like a little practice. So sometimes I have to like double down in some of the things that I'm going to ask because there's only so many problems I can ask. All right, so in terms of the setup for this, you have to kind of like run through a little story, right? Like, okay, this thing is gonna land, and just before it lands, it's gonna have a velocity that is gonna be both in the x and the y direction. We're okay with that? Because it's gonna have the same x direction velocity in the beginning at every point, right? It has no reason to reduce. So I might say, I'm gonna decide, just to give myself some numbers, I'm gonna call that 1, I'm gonna call it 2, and then 3, right here. So 2 is just before, 3 is just after, and I'll call this one 4. So in terms of like how the step-by-steps on how I'm thinking of this is very much tied to the steps, that numbering, that thought process. So I'm gonna have to ask myself, how do I get from 1 to 2? And honestly, there's actually like 2 separate ways. We had one way that we learned from the first part of the semester, just constant acceleration, right? It's gravity. So we could find what the velocity at 2 is going to be in the y direction. We're okay with that? Which equation would you use? And this is not a criticism, Cameron, but I see you looking for the equation sheet. I would say there's a certain amount of helpfulness to memorizing some stuff, right? And
there's a lot of
I
stuff.
know, I got you, I got you, 100% agree. And I gotta tell you, as a musician, I really need to be listening to my own advice here. It's better that I would memorize the lyrics, right? But I always have the lyrics in front of me, so I never actually memorize the lyrics because I have an iPad with the lyrics in front of me. So like sometimes I'm just encourage you to help you with your speed on an exam. For some stuff, maybe we call, I don't wanna use the word basic, but for some more of the foundational stuff, or some of the stuff we use a lot, sometimes it's gonna be a little bit better to memorize the thing, right?
Well,
So-
I'd start out with working energy, right?
What's that?
With like the KE plus P.
That would definitely work. You're right. I was
That's-
first though. I was gonna tell you that maybe we want to take a look at this guy right here, right? And we go two right there, delta one. I'm putting the stuff in that we would want right here, but that's not what's on the equation sheet, right?
Okay, I was gonna ask if that's.
That would be the one that I would memorize. And I'm not criticizing you, Cameron.
Okay.
I'm just trying to give you advice in terms of like the thing that if you could go to that, you could save yourself a little bit of time because you take time searching through the equation sheet. And some of it is confidence, right? They might have gotten it wrong at once or time, but it's fine. That's what the equation sheet's there for. But I'm just trying to be helpful. A lot of times time is the thing, and you also feel rushed. Even if you did have enough time, you might feel rushed towards the end of the exam. So you could find some way to shave some time off if you have something that you go, I know that one. I know that one. It also can help you, just feel a little more confidence. The memorization can make you feel more confident. Yes, sir.
Can you just throw the question back up?
Okay, sure.
Thank you.
You can see what I did right there, right? So I was able to get that velocity just at there. But you just mentioned work and energy. We could actually use work and energy to solve this if we want to. So let's try that one too, right? So we're gonna go, I can't remember, do I go KE first? Yeah, I do, right?
Yeah.
Okay, the KE1 plus PE1 plus U1 to 2 is gonna be equal to KE2 plus PE2. I'm saying this and I'm about to backtrack. It would work. I shouldn't do this. I should not do this. Probably, it's not a great example to do because I wouldn't. I just don't want to make confusion. So this is not going to be officially true. I want to take it. No take backs. I'm going to take it back because I don't want to include that. And then if I did that, I would say, well, if it was in one direction, but I don't want to tell you it's not one. I would get the same answer. By the way, I would get the same answer, but it's not appropriate to do. So I don't want to teach you something that's incorrect. So I could do this, but it would not be correct. The best way to approach this is what I had mentioned before, is that I would say maybe V2 in the y direction squared is going to be equal to V1 in the y direction squared minus 2g, it's supposed to be a g, delta y a 1 to 2. That's a terrible g. Let's make a better g. So it doesn't look like a y. It looks a lot like a y anyway. So just turning that thing around, we get this square root. Noticeably, you might think, oh, this is going to be, because we're going to, so it's got 0 in the y direction starting up right there. So you're going to have a negative 2, 9.81. Make sure you get the right, it'll just be like a minus 1 point to get the wrong acceleration of gravity, but it's incorrect, so I take off something for it. It's like, hey, reminder points. But remember that this is in meters, so we have to use 9.81. So go ahead.
Would that change in y be negative?
Yes, exactly. That's the reason why we're not going to take the square root of a negative, is because we went up from high to low, right? So the second one is the one we're going to go. We'd go y2 minus y1, so then it'd be a negative, right? y1's larger. So we get that it's 3.431 meters per second. No, start. I jumped down, sorry. 5.603 meters per second. And now we could actually jump ahead, right? We could actually jump ahead to from 3 to 4. Do you recognize that? Maybe that's not something you would recognize. That you go from 3 to 4, and we could figure out, because we know that it's going to peak at 4, so
it's
0 velocity in the y direction at 4.
no so it's got no kinetic energy.
It might have some kinetic energy, I'm sorry, because it's still going in the
Oh, but,
X direction. That's the reason why I crossed
But
this
you
out
can-
right here, because the X kinetic energy, I didn't want to include it.
Okay.
This should be the total stuff going on right here,
okay,
so it's not gonna help.
that's everything, but you
That's
can set it up with the velocity equation at 0 and have
Yeah,
this that you're solving for V3.
Yes, exactly. So did you see what he just said? He just did the aha thing, so he just got it, but I want you to get it too, right? We could use this again between here and here.
Don't you have a coefficient of restitution?
We do, but we know how high this went. They
Okay.
told us how high it went.
So you're saying that because we have that information.
So he jumped to it, but we have to find other ways for you to jump to it, right? If you didn't jump to that, to that thing, that go, oh, I see. The fact that they told you how high this went will allow you to figure out what the vertical velocity must be at 3. And you know it's gonna be less than 2, right? Because of the coefficient of restitution, right? Think about that coefficient of restitution as being something that's going to reverse the direction and slow it down. Especially when it's something with a really large mass, right? But we're gonna see that's actually gonna come into play here in a second. That's why she put it on springs and actually gave you the mass of this. If this was the ground right here, we would get the coefficient of restitution really quickly, right away. Because it was just gonna be that and that, those compared to each other. But now, because this thing is on springs, we're gonna have to do a little bit more work, but not a lot. Just a little bit more. But that's the thing this is measuring. That's the thing this problem is measuring, is your recognition of the situation. Right, that we have the velocity coming in, and we're able to figure out the velocity coming out, and that's gonna allow us to be able to work backwards and get the coefficient of restitution, and also figure out what the velocity of this block is gonna be, just after the collision. Does everybody know what we have to do from here on out? I see nods, but some not nods. Like what the next thing is going to do. I mean, this is the thing that we're measuring in an exam, right? Is the I see what's going on here. So let's talk about what's the next thing we're going to do. You know what we're going to do, right?
Well, I just have a question. The change in y, because we're looking at it from 4 to 3, would that also be negative because we're going backwards?
No, but we're going to have 0 is equal to the velocity at 3 squared.
Minus 2 times gravity times.
Yes, and they're going to jump over onto the left-hand side, so we
Yes.
still don't have to worry about the square root of a negative, if that's what you were asking.
Okay, yes.
I know this may not make sense.
It's okay.
Probably is wrong, but.
Other people probably have the same question.
No. Is the velocity in the y direction in this case the same as the normal velocity?
Yes, exactly, yes.
Okay, now I understand. Thank you, because then we have to take the coefficient of restitution, you need the normal velocities. That's why I'm like thinking, why are we using x's and y's when we normally have been using the normal and tangential like this? So I just got confused.
All right, so if you're still confused, what you have to do, just remember this, that it's okay. You didn't have an aha. You just keep proceeding with the problem, with the stuff that you know, and an aha moment's gonna kick in a moment. Okay. So let's go ahead and say, hypothetically, that we did recognize that we're going to be able to find the velocity of 3. So we write the velocity of 4 in the y direction is going to be equal to the velocity in 3 in the y direction minus 2g, and that's going to be, and I should write this out. Sorry, the delta probably doesn't help us out. It's going to be y4 minus y3, all right? And we consider that y3 is going to be 0. It just makes sense that that's a good place to make 0. And this is going to equal 0 because it's going to reach its peak. So 0 is equal to v3 y squared minus 2 times 9.81 times 4, which is 0.6. So we'll get that the V3 is equal to 3.431 meters per second. And this is the normal direction, as he mentioned, right? Because you could see that, and I think it's best when talking about the normal direction that maybe we write out our 3 diagrams. And I know for sure the direction these are going to go in, right? There's no question. So this one was down that amount, and we'll call it, I'll call it the ball. Does the ball have a name? No, it's called MBV. We should probably have given it a name somewhere along the lines here. I'll go V2Y, and then this is MBV2X. It's not necessary, but it's true, so that's why I'm leaving it in there. Right? I didn't want to. Okay, so we're going to have this explosion right here. And by the way, if we were going to be completely accurate, we would put weights into all of this. And you might want to think, well, is the spring going to be exerting a force? Well, yes, but it's going to be a small force compared to this impact. The weight's going to be equal to it. Until it actually has any deflection, those springs, their force doesn't change. It's kind of a weird thing with springs. We could actually make some mind-twisting problems with the springs. We'll do it later. We'll probably come up with rigid body kinetics and show you a couple like crazy things about springs, that their force is completely dependent upon their amount of stretch. So they're kind of like different than holding something by a string. If you hold it by a spring, like the string's tension will change, but the spring's tension won't change because it's all dependent on its deflection. But never mind. So we have there, so when we're done with the thing, we're going to get an M ball V3Y, but we're still going to have this guy, M ball V3X. We know that's going to be the same right there. We don't have to worry because nothing happened in the X direction. But here's a weirdness that we have to address. And what do they call this? A plate? Plate, yeah. So MP. And then we'll go VP3 for whatever reason. All right, so I kind of wanted to make up here I already named these just the velocity. I wasn't specific about what thing it is. I might even stick a B in there just to keep track of that. So if we do our impulse and momentum, I should really write out what the equation is that I'm going to use. And we're going to say that's the big equation. So here is the specifics, and I'm going to abandon the symbols here and just go with what's actually taking place. So we have the marble is 75 grams. So it's 0.075. And did I decide? Yeah, okay, I went with its velocity. We got up above. Negative 5.603. And so in the y direction, that's the entirety of the momentum. We know that the impulse is going to cancel out in the y direction, so it's going to be a conservation. And here is where we're going to have a little bit of more complication here. We're going to have 0.075. We know this velocity, That's going to be, where did I put it wrong? Did I put it, right there it is, 3.431, and it's positive. And then I'm gonna have a minus, and that's good because of the direction I know this plate must go. And the plate's mass is 0.4, because that's 400 kilograms, 400 grams. And here's a velocity I don't know. VP3. You can see we could find VP3, right? It's going to be 1.694. And we expect it to be considerably less. I guess it's not that less, but it is less than the velocity of the ball after the fact, right? Because this one's 3 and that was. And then we have the last part where we asked for the coefficient of restitution. And we know that's going to be E, and we have to remember the order in which these show up, right? We don't even need the equation sheet for this because we know the concept, right? We know that it's going to be the relative velocity after the collision divided by the negative relative velocity before the collision, right? We have to make sure that we swap which ones that we're subtracting from, right? So let me, if I write this out right here, let's go VP3, right? So that's this guy right here. And we don't change the signs. Don't change the signs yet until we put the numbers in. Minus the relative velocity here, which is going to be V, let's call it B3. Right, so I mean VB3 right there. Divided by VB2 minus VP2. So the very important thing, these guys switch positions. We're okay with that? So we have this guy, and he's negative, right? We just found him. Negative 1.694 minus this guy VB3. We found, we knew him. He came to 3.431. And he's positive, but of course we're subtracting because it's the relative velocity. And then we have VB2, which is going to be this guy, and he's going downwards, right? He should be a negative 5.603. And then this plate's not doing anything, so the plate at 2 is 0. So you see we have negative and negative, so that's going to be a negative number on top, but we have a negative number bottom. Okay, the coefficient of restitution should never be a negative value. And we get this, and we get 0.9147. And it should always be a number that's less than 1. So this is a really good problem from a professor's point of view, because it's not trying to trick you, but it's trying to put you out of your comfort zone. It's not identical to another problem you've seen before, so it makes you see, do you really comprehend? I don't want to say understand, because that's a dangerous word for people who say, I understood all the problems. I'm like, well, no, can you pick a problem apart, recognize what's taking place, understand what principle is underlying, and then get to navigate your way to an answer? Can you problem solve outside of memorizing the steps? The steps are different.
So in this problem, we're not worried about the x direction because the plate only moves in the y direction.
Exactly. Yeah.
So just eliminate, and that would be standard across the board if there's a problem like this. If the object that's being collided with is only moving.
I don't know if we're going to have an identical problem like this, or there would be another. This problem is somewhat. It's a well-formulated problem. I in hindsight, looking at the problem, I'm like, yeah, that's actually a pretty good problem because it's doesn't give you the same things that you got in the others, and you have this attribute, which is definitely a thing. I would tell you, okay, also, I'm gonna go on a side thing, so I don't think I answered your question, okay.
No, you did. That's,
A side thing I would say to you is if you don't recognize this and you're stuck, don't sit there and waste time. Well, no, sit there a little bit. Don't just give up. But come to the professor in the front of the classroom and go, I'm missing something. I'm missing something. And chances are, because I don't want you to leave a blank page, I'm going to nudge you in the right direction, try to get you to go, oh, I got it. But if I don't nudge you enough and you go back to your seat and you just don't get it, don't be afraid. Come back and ask again. All right? You won't upset me. Don't worry about upsetting me. I got to tell you, I got to give you a testimonial. I don't want you to do this, but I gave him infinite time for the final last fall. That was a struggling group. You guys are doing better than that last group. That group last fall was kind of soul crushing. But that's all right. You guys are doing well. You're
How many
progressing.
dynamics classes are there right now?
There's just one. You guys are the only class.
This is the only people take that.
Yeah, this is the off semester one. It's a tough. A lot of times this is just for various reasons. Yeah.
and having all summer, mental exercise.
Exactly. Yeah. And you took statics as somebody else.
3 classes.
Sometimes you took, some people have taken dynamics before, and they already turned off to it, so they're already in mind. There's all kinds of combinations why people don't succeed. Sometimes it could be attitude, work ethic. It could also be, it's just the time in your life when something is going to start clicking for you. I know I just had this discussion with another student that I had to, unfortunately, didn't make the great grade in for the fluid mechanics, and I had to drop him, and I felt terrible. But I told him the same story, like my history. You don't need to hear my life story, but I struggled with stuff. Things didn't come easy to me at all. And then until it actually start. I turned a corner. My brain matured from 18 to right around 20. And then the things started to become much more clear, and it happens for different people, right? And so hopefully that's an encouraging thing, right? That you're not, if you feel like, you might say, I'm this way, and I hear people say that with all kinds of reasons and things, and they're like, well, yeah, that's just the way you are right now. We're here to change, right? We're here to grow. We're here to become learners, right? And we're learning to learn. So no, yeah, you might be that way right now, but don't pigeonhole yourself and say I'm this way, because we're here to change it. All right, so maybe we take a look at another kind of problem. How about this is a type of problem? We'll go rando, and we'll only start it. What do you think? I want to try this out. So let's go for Newton's second law. And by the way, that's kind of a cheat because we're already going into the book and we know what kind of problem it is. But let's look at a sample problem. This is something I want you to mirror this. Take a look at the sample problem. Don't look at the problem. So we have a block B, has a mass M, can slide freely on a frictionless arm OA that rotates. Good period. You can see all my liver spots. Is that from drinking too much? I don't know. In a horizontal plane at a constant rate, theta dot 0. Knowing that B is released at a distance RO from O, expressed as a function of RA, I don't like this problem, component VR of the velocity of B along OA, the magnitude of the horizontal force F exerted on B, these are magical words, on B by the arm OA. Okay, so let's write this thing out. Okay, so our reading comprehension is being tested here. So I always, because maybe that's my thing, I like making drawings. So make a drawing of the thing, try to kind of get it out there, and try to see what they're saying. OA rotation. So it says that. So it's a constant. Okay, so let's see. It's a constant angular right there, right? So a block B has mass M. I don't like things that don't have numeric answers, but this one does. Can slide freely on a frictionless arm that rotates in the horizontal plane. So that's sort of important right here. We're looking down at it. So gravity is not a problem for us, right? And it's at a constant rate. So that thing is constant. Knowing that B is released at a distance RO, so it's released somewhere right there, and then it's going to move out onto there, right there. Express a function, so we want to do like a find. So we have A here, and so we want VR as a function of R, right? So that's what they're asking right there. They're saying that this is how they're phrasing it. So they want A, they want the component VR of the velocity along B, OA. So expressed as a function of R. And then the next one, we have the magnitude of the horizontal force F exerted on B by the arm. So for B, we want to find F also as a function of R that's being exerted from the bar onto the thing. So we want to, I think the first thing we want to do is draw the FBD, IBD. Remember, it's in the horizontal plane, so we do not care about gravity. When doing this, something I don't emphasize enough is what's going to help us is to establish what is our coordinate axis. So what kind of a problem is this? We haven't said it out loud, but you might already know. What category? It's true. Anything in particular about it? What coordinate system? Polar, right.
I guess there.
Yeah, but you see the R, and you see the theta dot, and you say as a function of the radius, right? It kind of lends itself to being a polar coordinates problem. So R must be aligned that way right there. Call it ER. And then E theta is always 90 degrees and pointed to the left. I'm looking at this, I don't like it. So if we were to take a look at this and draw the forces that have to be acting onto this. Well, they didn't say anything about friction, or did they say it was, no, they said it was frictionless. So is there any forces in the R direction? There's no gravity because we're looking down at it. It's in a horizontal plane.
Oh, okay.
So there's no forces in the R direction. We have to kind of like work our way through that. I like to, by the way, when it's a collar like that, I like to kind of like make it sure that we see, kind of thinking about those lines. And there's no friction. So the only force on this is going to be in the transverse direction, let's call it the theta direction. There should be a theta, not a zero. And this is the bar, so this is going to be F, we call it F theta if we want to, but it's the only force that's acting onto this. Now, when it comes to the accelerations, we don't quite know what they are. So let's go ahead and put them in the positive direction here. We'll take the mass times the acceleration in the radial direction and the mass times the acceleration in the theta direction.
It'd be a lot better if there was numbers.
I hear you. I hear you.
Like,
There's a lot of math. There's a lot of
It's hard to
dynamics
follow.
classes. It's actually maybe it's good to be out of your comfort zone a little bit, not too long, just enough. Numbers are. I agree with you. I prefer the numbers. Let's go take a step back here. A little aside. Says recall. You can spell recall correctly. That's sad. That the acceleration in polar coordinates is r double dot minus r theta dot squared er plus r theta double dot plus 2 r dot theta dot e theta. Squeeze it in there. Squeeze me right in there. So right around there, you might start getting some. Oh, I see what's going to happen here. Maybe it's going to start soon. Remember, we want to try to get VR. Remember? What is VR, by the way? You remember what VR is? Let's go velocity as a function in polar
It's
coordinates.
just R dot, right?
Yes. Thank you. So this is an aside, but we'll go right here. Let's take the sum of the forces in the radial direction equals mass times acceleration in the radial direction. We already established this must be 0 on the left-hand side. There's no forces in the radial direction. So how is it possible to have that right there?
acceleration 0.
Yes. Okay, but what does that mean up here?
That all the acceleration is going to be in the other direction.
It means we're going to be able to find out what r double dot is.
Do we have R?
R is a variable. Like R starts at RO, but it's going to vary as it goes along. Like you can imagine this thing is going to be like a color. Let's like try to like a zoop, right? That color it's gonna want to go outwards. You can picture that, right? As this thing is swinging, that this little thing is going to start going from outwards.
Like away from the baseball bat?
Yeah, like that. If it was loose. Yeah. Yeah, like a donut. So we could actually find what r double dot is going to be equal to. But we don't really need that for our thing. But this is something that we can confirm that that theta dot is something that we're going to be given, right? Because it's constant. We're also going to have to say that still not liking this one. Okay. Some of the forces in the theta direction is going to be mass times acceleration in the theta direction. Sorry. All right. So we're going to say that our F, and this is actually the F that we want to get down here, by the way. It's going to be equal to, all right, so that's the only mass, and we drew it in the positive direction, so we're okay right there. It's going to be mass times, and then we know this can be R theta double dot plus 2 R dot theta dot. But that's going to be equal to 0, right? Because they said that this was going to be constant. Let's put the 2. I'll put the 2 in front. And I'm really regretting, after I read this, what their strategy is for the thing. All right, so I'm a little bit stuck, but go ahead.
Doesn't that say that a single dot's 0, not theta double dot?
Why?
Why'd you make theta double dot equal 0?
Because the problem said it was constant. Theta dot was constant.
So you crossed out theta double dot.
Yeah, you cross out theta double dot, not theta dot.
If the velocity is constant, that means it's not accelerating.
Oh, so that means there's no.
That means
Yeah,
the
yeah, so-
velocity exists, but the acceleration.
Yeah. So so it's the same thing true with the angular. Angular velocity is constant, so the angular acceleration must be 0, right? Here's where the thing gets kind of ugly, and like I said, I'm somewhat wondering if I'm going to cause myself a lot of heartache here. Fudge. Can't do that, man. I'm almost going to stop myself from going any further. I'm just about to. All right, so I don't like what their approach onto here, and I'm not sure why they're going to try to teach us this. It's too narrow of a thing. I'm totally was taking it on faith that this was going to be a good problem, and it's not a good problem.
I'm beyond confused.
Oh, gotcha. Okay, but I don't know what are you confused by right now? I'm sorry.
Like, why are we solving for force as 2R dot, theta dot? Like, how does that force?
Well, the truth is they're about to do something. They're about to do something that's relatively clever here, and I'm trying to see how live here how I'm going to try to explain it to you. I could just write what they did, and I think it would just boggle maybe a little bit. They're saying that remember that we're trying to find VR, and we know that VR is equal to R dot, right? So they're also saying, well, something that we had up above R double dot. Another thing that we could say to that's going to be VR dot. So what they've decided to use is sort of a niche type of thing, where they're saying, well, that's the same thing as saying dVr dt, and therefore, because the hint that you would get is that this thing is a function. That means it's a function of r. So is there a way that we can modify, get away from things being a function of time and turn them into a function of r? That's the clue that they have buried in there. And any time that we're doing that, one of the methods we have is the chain rule. That we could take, if we could break this into, turn this into dV r dr is what we would rather have it be. So we could say, well, the only way we could do is go dr dt. So we know that right there is actually r dot. right? So that's the thing up above that we said, oh, we could take this chain rule, so that chain rule, a little joke. So now we have dVr dr. And by the way, that should be a little bit reminiscent. Yeah, so this is like a little bit reminiscent right here. So we said that r dot can be turned into that right there. And therefore, the thing we used up above, we could substitute in. Once again, this is the type of problem that gets taught in a lot of schools. So we know that r dot is going to be r double dot is equal to r theta dot squared. So what we could do is we could substitute this back into here and say r dot, or I don't want to do that. Yeah, it's a proof. This happens in a lot of things. I'm not gonna make excuses for other people's stuff, but it's kind of.
I'm getting where you're going now.
I got you. Yeah.
You've like worked it out.
They're able to manipulate this and get this into a function of the thing. So I'm not gonna go further with it. It's not useful to the preparation of our exam. We're not going to do anything along those lines. But that's what they did there. I'm just explaining what's taking place. Let's pick another problem. I'm sorry this was a distraction onto the list.
That was a lot.
That was a lot.
Didn't seem like much, but it was.
It wasn't as useful as I had hoped. Let's take
Spinning ball.
spinning ball. Let's do a spinning ball. All right. So but unfortunately, this one too does not have numbers in it.
I don't want to know.
You don't want it if it has. I got it. You see the same issues.
Someone else pick a problem.
Yeah, someone else pick a problem. Okay, that's good practice. They're much better, well vetted. Okay, so you have something from there?
Let's see, a work energy one.
Let's do a work energy problem. I agree. Work energy.
Whichever one. Let's you must use work energy principle 7.5 pound collar. That one. Yep, right there.
There you go. Okay. Thank you.
There you go.
Edit that video out.
Let me get a picture of it.
It is on the internet.
Yeah, but the internet's bad.
Is it?
Internet's always bad.
Okay. You must use work energy principles to receive full credit. A 7.5 pound collar is released from rest in the position shown, slides down the inclined rod and compresses the spring. The direction of motion is then reversed and the collar slides up the rod. Knowing that the maximum deflection of the spring is 5 inches, determine the following: the coefficient of kinetic friction between the collar and the rod, the maximum speed of the collar. All right, so once again, we've made like sort of a twist on problems that we're maybe somewhat familiar with. Not too much of a problem, not too much of a twist, but just enough that we're not in our comfort zone. There you go, something like that. So, let's see, other information. We know that the spring constant was 60 pounds per foot. We know that the distance before the compression of the spring was 18 inches. And we know that this thing's at a 30-degree angle. And it's 7.5 pounds. And it's released from rest. That's good news. And that it compresses the spring. So, the max deflection is equal to 5 inches. Why did that come out again? What is going on? Why does that thing keep coming up? Move, get away, go, the mouse. So what I would do is I would draw another picture of this to try to work through and kind of tell myself a story. So I'm going to put the picture is going to be of this thing after it's been compressed. Right, so it's compressed 5 inches. And there's an additional, and we're measuring it from the bottom, let's say the bottom of the collar. So up here was where it was before. right there, so there's the 18 inches. So we'll call this one state 1 and this state 2. And maybe you want to, right here, mark that as the datum. So in terms of the kinetic energy at 1 plus the potential energy at 1 plus the work that went between 1 and 2 equals the kinetic energy at 2 plus the potential energy at 2. And we know that the kinetic energy at the beginning, because it starts from rest, is going to be 0, right? The kinetic energy at state 2, because that's going to be the maximum spring deflection, is also going to be 0, right? We're okay with that? The potential energy at 1 is going to be gravitational. But then at state 2, we consider that the datum, but it still has potential energy, right? Because the spring has spring potential energy. So a lot of times what I will do is I'll write out this as a list. It's just helpful to me as to, in terms of like, you know, I say there's not step-by-step things, but there are certain like procedures where I go, this is going to help me logically pick this thing apart and think my way through it. So I said the potential energy at 1 is going to be mgy, but this thing is in US units, so we could go, it's going to be the weight times its delta y. I'll go delta. So it's going to be, don't really have room to do this thing, but I could have found out ahead of time, maybe when I was working up to here, I could find out what my delta y is going to be, right? It's going to be my 18 plus 5, or 23 inches, divided by 12, times the sine of 30. Is that true?
Yes.
So it's going to be my 7 pounds times the 23 divided by 12 times the sine of 30. I guess I could fit it in. What is my work and energy going to be? My work. Go back to what the problem is asking, right? It wants the coefficient of kinetic friction, right? So it's going to be frictional, right?
Negative F.
Do we know the friction force?
No.
Do we know the distance though?
Yes.
23 divided by 12, right? 18 plus 5, that's the distance it has to go through. We already said the kinetic energy at 2 has to be equal 0. And then the potential energy at 2, we said that was going to be spring, right? So 1/2 K del 2 squared. But we were given that del. So it's a little bit different than we've had before. Lots of times we want to find that del, but we were told that we had that del. So 1/2 times 60 times 5 divided by 12 squared. By the way, I'm just making this in this list. That's simply from my comfort zone. I like doing it that way. You could have just written it out this way or across here as you started to think your way through it, right? So, and I didn't bother getting any in-between numbers. I usually do, but wouldn't do it during an exam necessarily.
at 7, it's supposed to be 7.5.
Is it 7.5? I'm sorry. I was probably talking while I was wrote half of it down. Thank you. And I'll get a friction force of 1.033 pounds. And then to get part A of this, I need a normal force because they want the coefficient. They want the coefficient of friction. And I'm going to go ahead and draw the acceleration in there, but we don't really need it. And I decided to go this x prime, y prime, so this is acceleration in the x prime direction. What all I really need is the summation of forces in the y prime direction. I'll write it down, but we know that that's going to be 0 because it's not coming off the rod anywhere. There's no y prime direction here. Recognize that angle right there must be the same as that angle. I'll put in my positives that way. So we said Fn minus the W should be cosine tan equals 0. Fn is equal to 7.5 cosine of 30. So therefore equal to 6.495 pounds. So coefficient of kinetic friction, friction force divided by normal force. So now it is asking, part B, the maximum speed of the collar. What do we do for that, do you think? So how do I determine the maximum speed of the collar? Isn't it going to be when the kinetic energy is the maximum?
Just before it hits the spring.
So when's yeah, he's got it right. But why is that?
Maximum speed, just before it hits the spring. Because the spring has a counteracting force.
I think so, yeah. I would also say that's probably when the potential energy is going to be at its lowest. Can't say that for sure. But the gravitational potential energy has been reduced a lot, but it's going to start reducing after it hits the spring. It's going to continue to be reduced, but the potential energy is going to start increasing of the spring, right? And that's going to be by the square. So that, the logic goes, it must be before it hits, right? So in order to do part B, we actually kind of need some of this from part A, right? We need this because we're going to say maybe reset the datum or redraw this thing out. So now this is where we started right here. And now, so this delta y is going to be different. We could reuse different numbers maybe before this, like, you know, because this is actually happening before state 2. So maybe I'm going to go ahead and renumber. This is still state 1, but this is the new state 2. The state 2 that happened before the previous state 2. So this is simply going to be 18 divided by 12 sine of 30. And so now KE1 plus PE1 plus U1 to 2. And these are all different new 2's. So this KE is the thing that we want to try to find now. And because we're going to reset our datum, that's going to be 0. This is still going to be 0. And this is going to be a new value. And this is going to be a slightly new value. So we're going to say 0 plus the weight times the height change, that delta y, 18 over 12 sine of 30, minus the friction force, which we know is 1.033. And we know it's got to be the same, right? It's got to be the same in the beginning as the end. There's nothing that's going to, no reason for it to change. The normal force hasn't changed. The friction force has to stay the same. The distance is going to be 18 over 12. That's the distance that is traveled just before it hits the spring. And then it's going to be equal to, you have to be careful here, 1/2. Remember, the mass has to be divided by 32.2. I mean, the weight has to be divided by 32.2 to get the mass. One half mv squared. So just before it hits the thing, it's going to get 5.916 feet per second. Let me do a problem that I haven't done from an exam that I'm not going to give. Another working energy problem. It's too difficult. I have a picture of it. All right, so here's a working energy problem that I created or adapted, where I had a collar, another collar problem, and it's got like a little, thing where the string is attached. It's riding on this rod right here. And when the collar gets up to right here, oh, didn't make it. Okay, pull that right there. It's attached to a pulley, and somebody is pulling a string with a constant tension. So when it starts, it's like right there. This thing is at an angle, and there's a spring. Let's see, make sure that's ghosted out. There's a spring like that right there. So that spring just happens to be right up to the spot where the center of this is going to be when this thing is perpendicular to it right there. And that distance is something I called B, from there to there. This distance here to here is something I called C. That distance is D. And I said that the weight of this collar is 6 pounds. This angle is 35 degrees. This distance, D, this right here, that's the half width of this, is going to be 5 inches. The tension on the cable is 50 pounds. And the other dimensions are B is equal to 30 inches, C is equal to 40 inches, and then the spring coefficient, the spring constant is 100 pounds per foot, lbs per foot. And we want to find, and if this is 2 right here and this is 1, find V2.
I missed the first part of the question. So that's a string attached to a collar, and they're pulling the string and hitting the spring.
Yep.
Am I looking at that
And
correctly?
at state 2, notably, the string on this from this pulley is perpendicular right up here, right? In other words, that spring is going to be compressed the dimension D. Can you picture that?
Yeah, it can only go as far as the perpendicular line of the pulley.
Yep.
Well,
I mean, no, that's the state where we want to find it. It might continue a little bit
yeah,
up.
if you have a force, it'll go past a little bit, but eventually that's where the equilibrium is.
Sure. But all we really care about is when it just gets it up to 2, which is as far as it's going to go, for as far as we care. And I can tell you what really puzzled a bunch of people. I think, was there a coefficient of friction? I think I left out the friction, right? So this is frictionless. That's good news. And it started from rest. First off, if there was friction, why would that be difficult to do?
Friction
with the friction.
Force is changing.
Yeah, there you go. Force is changing, right? The normal force is changing. So the friction force changes because that angle of that string changes all the way through. But the first thing to do in this problem is just to set it up. What would I do? I know it's a working energy problem, right? I can tell there's a working energy problem because there's a spring, but also I told you it was a working energy problem, right? I'd probably tell you, hey, use working energy here, but that spring's a dead giveaway. We don't want to mess around, and it's also there's two states, right? So and we don't know anything about time. So impulse is going to be force times time. We need to know something about the time. We know about position, and it's got a spring. So that's definitely a working energy problem in terms of problem identification. But let's talk about some of the particulars and the tricks that might be hidden in here. So here, in terms of our problem-solving strategy, is to write that out and then start picking it apart. So what's KE1?
0.
Yeah. Starts from rest. What about PE1?
Couldn't that also be 0?
Yeah, so that's a good place for the datum, right? What about work? This is a big trick.
Tension on the string.
Okay, tension on the string.
Gravity. No, not gravity.
So what is work though? He said the tension of the string, so that definitely, that's it. So we need to go force times the distance, right? So we have the tension. So what? Is it going to be? One thing is that on your equation sheet, or it should simply be the integral of f dr, right? And this should get a dot right there. And what I just did right there is a dirty trick because that was distracting. I'm distracting you. I put it there. At least I'm thinking out loud. There's the thing there. That's going to lead you down a bad path that would prevent you from getting the trick. But it also really messed with some Yale people when I gave the problem at Yale. Because they didn't recognize the trick, but they also surprised the holy hell out of me in their calculus skills. Because the orientation of the string is always changing as you move along. And so the angle that's in here is always changing along the way. So what you actually have to do is you have to take an integral of a tangent with a cosine inside the tangent. And they were able to do that.
Sounds fun. Is there a way to not do that?
Yes.
Because that would be terrible.
That would be awful.
This
A
would
terrible
be-
thing. I would never do that to
This
anyone
is-
on
this is
purpose.
the
What
way
I
to
wanted
do
them
it.
to do is just to but I only made it like 5 points silly to get that wrong. It's okay. So you made 95 on the rest of the exam. It's good. But I just want you to recognize it. I think actually I made it 2 points when I was here. I gave the same problem here. Just see. I want to see what would happen. Also, I want anybody would ask. Anybody that came up to me, I'd tell them what it was. I'd tell them what the trick was. Because they knew to ask. Can you figure out the length of the string before? And can you figure out the length of the string after?
Because you have C.
Now you know the change in length of the string. That tension is on the other side of that pulley, isn't it? You just need to know how far you pulled that pulley. The tension's constant. Is that bullshit? Is that bullshit? Is that unfair? I thought it was awesome.
That height stays the same, right?
Well, one thing, the orientation right here. You just have to go,
Yeah, but so that.
Is that
Wait.
bullshit? No,
It wouldn't sense.
Does it make
Wouldn't
sense?
that make sense?
Does it make you go, that's why I want to show it to you.
Wouldn't
So
that
like,
also just
I like
make-
the, I got it.
Wouldn't that also just make the length of the string at 2b?
Yeah, no. It was, so you figure out the length here, and then you subtract out b, right? So just go, c squared is c squared plus b squared, right?
Yeah.
And then subtract out b, and
Okay.
now you know
And now you
how
know
far
much
you pulled the
pulled.
string.
Okay,
and multiplied that tension by it, and you got the work.
okay.
But they just saw this right here, and they integrated that as it went up.
Yeah, I don't even
It's
understand,
constantly
I don't even
changing
understand
orientation.
how that would work. How do you take the integral of something?
I think I wrote it up somewhere, I should.
No, it's okay, no, it's.
I was just impressed. But that was one of the reasons why I tell you the story that like
Some trig sub integration, right?
yeah, well, I'm trying to remember, I think it was maybe tangent times cosine. Because you remember down here, the force is, the dr is constantly changing, right? So the only force that you care about is in this orientation right here. So you have to take this force times whatever angle that is. So that angle is constantly changing until it gets up to right there. Right there, right? So we have the beginning, so it's a function of the distance that is coming back into there. I'm trying to remember, I wrote it out somewhere.
Alright, let's just finish it the normal way.
Yeah, just do the normal way.
Let's just finish it.
So anyway, yeah, you should, so all you have to do is Ft, and you're adding, it's positive, right? Because you're adding energy into the thing. So you'd say that would be square root of c squared plus b squared minus b.
Are these numbers supposed to work out funny like that?
What do you mean?
Um,
So anyway, this ends up being, by the way,
I don't know, it just came out funny. I got 50 and the force is also 50. I got the hypotenuse.
well, it should be, this is going to end up being 20, right? Because you can subtract.
It's a 30, 40, 50 triangle.
Yes, it's a 3, 4, 5 triangle.
Yes, but that doesn't mean that you can just skip the calculations.
You could. Want to?
I always do, I see it.
I never skip.
So just 50 times 20 over 12. Better be careful, right? And the kinetic energy is what we're trying to solve for. So, 1/2, the mass is 6 over 32.2. We're trying to get the V2, and you have to, and the potential energy has two parts, right? The potential energy is going to go up, so we're going to have the weight of 6 times the distance, which is going to be C 40 divided by 12 times the sine of 35. Sorry. But then also plus 1/2 100 times the deflection, which we decided was going to be D, right? 5 inches divided by 12 squared.
Sorry, is the equation, is the thing right before also part of the potential energy?
Yeah, that's potential energy, and these are both potential energy. I'm
That's
sorry.
potential energy as the weight times height?
Yeah, this is weight, and this is the height, right? So 40 divided by 12, that's going to be C, but we're moving from here to here, right? So it's times the sine of the 35 degrees. I couldn't resist myself. I like this problem so much that it was like, it was really just that part of it up there, or I should say this part right here where I'm like, because it took me 8 minutes to solve, and I was like, that's the perfect time for me, right? Starting with the V2 is equal to 25.74. Now, a really evil problem was to add friction to it. That would be just evil, because then you really would have to do that integration thing that they were doing to be able to get the constantly changing friction force, because there's a constantly changing normal force. It's not very nice. So I'm not gonna ask that question.
Let's do one more question. Yeah, don't ask any of the ones that are like crazy like that. Has to be.
Well, I want you I want, honestly, what I want, at least out of a review session, is not to intimidate you, but to get you to try to think, right? Or to prepare you to try to have that hat on, that thinking hat, right? And like, I'm going to think during this, or that's my goal, that's what I'm raising to do, right? And, you know, once again, I'm also gonna tell you, I also wanna let you know that, like, hey, if you don't get the thing, ask, right? You know, we're trying to see, can you navigate a problem? I'm not trying to see if I can trick you, although that one was really the borderline of what I don't like that, but there gets to be a gray area, and that was a gray area for me. All right, so we're gonna pick another problem. We haven't done enough impulse and momentum. We totally had a big utter fail when it came to the Newton's second law. So. I don't know, let's see. Can we do, see, I rarely will do an oblique problem. I don't like oblique because they take a little bit long, so it has to be a pretty simple oblique problem most of the time for me. I've asked a bunch of, before, these kinds of problems right here, the bumper car ones.
Only one direction.
Yeah, so it's just there's a coefficient of restitution going on here, and you know, you get different masses. So you get two equations and two unknowns. It's fairly a straightforward problem. You know, it's not really any different from like this problem, right? The two steel blocks slide without friction on a horizontal surface immediately before the impact of velocities are shown. Knowing that the coefficient of friction here, find the velocities after input, and then the energy loss during the impact.
Want to do this one? Or you want to do the other one?
You could do the other way around too. So we could say that knowing that the velocity of block B after the impact is observed to be 2.5 meters per second to the right, determine the coefficient of restitution. Which one do we want to do? Want to do both of them?
As in both of these two? Or like the bumper cars and this?
We do it.
Let's do one of
Let's
these.
start with one of them.
So let's see. You get these blocks. And this one is 0.6 kilograms, and this one's 0.9. And he's moving at 2 meters per second. He's going at 4 meters per second. And he's A, and he's B. And this one, so 13,155 is to find, it asks for, they give us the coefficient of restitution is 0.75, and we want to find VA and VB2. We also want to find energy loss.
How do you
go to working energy, just like we did the efficiencies, right? We get the kinetic energy before equals plus the loss equals the kinetic energy afterwards. So we go MAVA1, MBVB1, kaboom, and then MAVA2, MBVB2. I think the best strategy is to always go in the positive direction after the collision. So I could put numbers in here too, right? That's not gonna hurt. And they're nice in the SI units. That's nice. So here though, make sure we get the signs correct. This is in the X direction. So it's gonna be a -2. No impulses, and so we have 0.6 times VA2 plus 0.9 VB2. So 0.64 times 0.92 times plus. So I end up with 0.6 on the left-hand side, 0.6 VA2 plus 0.9 VB2. And that's going to be equation 1 for us. 2 unknowns. We go to coefficient of restitution. VB2 minus VA2 divided by VA1 minus VB1, 0.75. And A1 is 4. And B1 is -2, right? And be careful of that, negative. So that's going to be +6. So we're going to take 0.75 times 6 is equal to VB2 minus VA2. Or 6 times 0.75, 4.5. Here's our second equation. So I think I'm going to solve for my VB2. I'll write it out. Skipping steps. I'm terrible at algebra if I skip steps. Not so great even then I don't. .9 times 4.5 plus point. I just skipped a step. I just jumped ahead. Sorry. VA2. There you go. Yeah, so that's what I was doing. Okay. I have to replace that bracer soon. So let's see, 0.6 minus 0.9 times 4.5. So I'm gonna get a negative number on the left-hand side. And so I'm gonna have a negative 3.45 on the left-hand side. It's gonna be equal to 0.6 plus 0.9 VA2. VA2 I can't add 0.6 and 0.9 in my head. That's going to be a negative 2.300. And then I could put it back into VB2. Get 4.5. 2.2. And these are meters per second, right?
Why are we including the 0.9 VA2 on the third from the, yeah. Right, but we just solved for VB2, so wouldn't it just be 0.9 times 4.5 plus VA2? Never mind, I'm stupid.
No problem.
Sure you didn't.
It's cool. These are good questions. Notably, let's take a reflection back here. We could see that both of them reversed course, right? VA2 is now going to the left where it started out to the right. But B is also going to the right, even though it started off going to the left. And we can see for the kinetic energy of the thing, we're going to have KE1 plus PE1 plus U1 to 2 is equal to KE2 plus PE2. There's no potential energy in any of this. But this is going to be the total kinetic energy that's in here, so 1/2. And I'm not going to write down the symbols, I'll just go put them in here. At 0.6 times 4 squared plus 1/2 0.9 2 squared plus 1 to 2. That's actually what we're trying to find. And then we have 1/2 0.6 times, it's negative, so we don't even have to put the negative in there, but I'll put it in there anyway. 2.300, did I get that right? Yep, I think so. Squared plus the 1/2 0.9 times 2.200 squared. So we'll say just 4.8, I think. So this is 4.8, this is 1.8, so they come out to 6.6 Newton meters worth of kinetic energy. This better be less, or we did something wrong. So this comes out to 1.587, like 1.6. And this is 2.2 squared, 0.9 times 2 divided. So it's like 2.2, thereabouts. So it comes out to 3.765. So the energy lost between 1 and 2 is going to be, so that ends up being negative 2.835 Newton meters. But I think it more informative is to take the kinetic energy at 2 and divide it by the kinetic energy at 1. So 3.765 divided by 6.6. So you get 57.05%. It's not a terrible problem, terribly difficult, but very, 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 very straightforward. By the way, if you haven't noticed, sometimes looking in the book, this is basically the same problem as the kid with the slingshot one. See, where would the ball hit the ground after bouncing? I just made a kid with a slingshot. We got time for one more, maybe? Quick one. Second one. Let's go pull. Let's go. One of those ones where, see, people have been stuck by this problem before, and I was like, you know, I think I didn't think it was as difficult, but this one right here, I think it's actually one of our practice problems.
Yeah.
So knowing that the swings at the amusement park ride form an angle of 40 degrees with respect to horizontal, determine the speed of rotation and the force of the cable of the swing person weighing 50 pounds. You know how you would go about doing that?
Yeah, you have the radius and the distance from the center.
So can you say it's a path coordinates problem?
Yes.
So you know, you'd set up the free body diagram.
Then you have to do a coordinate transformation.
Not really. Okay, now, you know, recognize that, you know, we're actually, the truth is, take a look at an individual person. You would have, this would be the tangential coordinates, and that would be the normal coordinates, right? But we really can't do much in that, so we want to actually kind of look at it from the side instead, and draw what this guy is like this right here, right? And draw what the tension is right in there. And so this is the FBD, and this is the IBD. And recognize that the mass times the normal acceleration is the acceleration we're looking at. We have the weight of a particular person on the swing, and so and then we have the angle. Yeah, so I think they said this angle was 40 degrees, right? Knowing that the swing in this park forms an angle of 40 degrees with respect to horizontal, determine the speed of rotation right in here. So what you want to do is go to the cable tension is actually probably the way to go to start with this, right? That we can get the sum of the forces in the, let's call it, because I want to call that the normal direction. Let's call this the y direction. And the y direction is going to be equal to 0 here, right? There's no accelerations in the y direction. So we could say, okay, so we get the tension, but that's going to be times the sine of 40 degrees minus the weight, which they told us was 250 pounds, right? So you get the tension. So just 250 divided by the sine of 40. So 388.9 pounds. And now go to the sum of the forces in the normal direction. And you know that it's got the tension, right? So 388.9 times now the cosine of 40 degrees is going to be equal to 250 divided by 32.2. That's the mass. And we can get the normal acceleration. So the normal acceleration turns out to be 38.37. Something we should look at though here, note that the tension up here was mg right in here, so it's going to be right here, this is actually mg divided by the sine of 40. And then when we put it in here, this was mg divided by the sine of 40, so that mg would have canceled out. Yes. And it would have been like the tangent, remember the inverse tangent, cosine over sine, right? This mass would have canceled out. Yeah, I think that's right, yeah. We would replace that over there and the mass would have canceled out. The gravity would not have canceled out. So, but anyway, what we would have been able to find is that acceleration, the weight, we didn't even need to give it to you, right? Except that they ask you for the tension later on. But now we can find what the v squared over the radius is going to be. Got to be careful. The radius is going to be, this is the only difference in this problem. It's going to be 20 feet plus the, whatever the, I guess 15 times the cosine, right, of 15 feet. 15 times the cosine of 40 degrees plus 20 is going to be the radius from here to the center, that radius that we would use right in here. So be 20 plus 15, I think I'm right, it's the cosine of 40 degrees squared equals 38.37 feet per second squared. And now we would be able to find what the velocity of this thing is going to be. And so what I'm going to do, 20, 15, I think I just knocked the thing out of my stack, but I think I'm right. Cosine times plus square. No, not square, dummy. Sorry, squared. That's not squared. There's no reason that'd be squared, right? Because that's v squared over rho. This was not squared. So I get 1.104 feet per second from that, right? So and you know what I did? I just screwed that up. I just divided. I'm sorry, my brain's not in it. 15, 40 cosine times 20 plus multiply 38.37 times square root. That makes more sense. 34.76 feet per second. And then if you want the tension, well, we already told the tension, right? The force in the cable for a person, for a swing and person weighing 250 pounds. Yeah, so we got this one first. We got that one second. The good thing on this is that's a short problem, but it's not that much different from like this. You know, this is basically the same problem as that. We did this one, right? We did this one as a homework problem? Yeah. All right, I'm sorry about that example. I should have vetted that thing out. I didn't realize until I got like 2/3 of the way through there they were doing some weird damn thing with that.
but it is.
I don't know why, I don't know what the point of that is in terms of,
Yeah, some
Edu-
of the,
educa-
some of the
education.
sample problems in the book are not super clear.
I think it's a much better book than a lot that I've